All right, let's go ahead and take a look at section 4.5, limits at infinity. All right, now just a reminder that it sounds a lot like what we did in section 2.5, but remember that 2.5 was finding the limit as x approaches some number, maybe from the right or from the left, and winding up having an answer that turns out to be an infinity. So the answers are infinity, where section 4.5 is finding the limit of a function as x approaches, say, a positive infinity or a negative infinity. So your infinity is here, and then your answer might turn out to be a number like 5 or -1/2 or 0, or you might even get an infinite limit like infinity or negative infinity. Okay, so you still can have answers that turn out to be an infinity. Okay, so 4.5 is the one where the infinity is what your x is approaching. Okay, so it's going to the right, bigger and bigger and bigger, or you're looking at x's as you move to the left and you get more and more to the left. Okay, all right, so we talked briefly about that, but if we look at this example right here and you think about it, 8 over infinity winds up being something that's going to 0. Okay, so because it's like, say you had 8 over 1, that would be 8. 8 over 2, that's smaller, that's 4. Okay, let me get a lot smaller. How about making it a lot smaller? How about 8 over 8? So here you're 8, here you're 4, here you're 1. Well, that would be down to a 1. If I did, say, 8 over 10, I'm at 0.8. If I did 8 over, let me jump a little bit, 8 over something like that, well, then I'm going to be at what is that? 1, 2, 3, 4. I'm going to be like that. And so you wind up getting the whole expression, it winds up approaching 0. Okay? So a fixed number on top over an infinity on the bottom winds up going to 0. All right, so kind of helps to remember that. I'm going to jot that down up here. So if you have some kind of fixed number on top, so you have some number on top, could be a positive or a negative number on top, and you wind up having in the denominator, you have either a positive or negative infinity, okay? All right, that's going to wind up equaling 0, okay? All right, it's the other way when you wind up having like a fixed number on top, and in the denominator you have a 0 in the bottom, then that's going to wind up equaling either positive infinity or negative infinity, depending upon some other aspects of it. Okay? That is a 2.5 situation. Okay? This right here is part of a 4.5 situation. Now your answers in 4.5 will not always be 0, but that situation is what would come up in a 4.5 situation. Okay? All right, so the other one, that number over 0, that was what's happening with a question like this one. So this would be 8 over 3 minus 3, which is an 8 over 0. So we talked about how at that point you know it's either positive infinity or negative infinity, and you got to think about which one. So that's when you look at how you're approaching 3 from the right. So you're approaching it from 4, and so you think about how if I plug in, say, a 3.1, I'm going to have a positive on top because it was just a fixed number 8, and then since I'm approaching from the right, I'm going to have, and I'm subtracting 3, I'm going to have a positive on the bottom, so I wind up having the final answer being a positive infinity, okay, as my final answer. You have to kind of do a two-part analysis. All right, so limits at infinity. Limits at infinity, it's really what's happening at the ends. Like as you go towards positive infinity or as you go towards negative infinity, what is happening when you're far away from 0, okay? So that's limits at infinity. So with this particular example, the function we have is 3x squared over x squared plus 1. And if we were looking at the limit of that as x approaches, say, positive infinity, what we're looking at, what we're noticing from the graph, is that as we let x go towards positive infinity, that our function seems to be getting closer and closer and closer to this horizontal line right here at 3. So the limit of the function as x approaches positive infinity would turn out to equal 3. And with this particular one, if you were approaching negative infinity, x was going towards negative infinity, you're still approaching that same horizontal line up there at 3. Okay, so if it were the limit, but x was going towards negative infinity, the limit of that function from the graph we can see would also equal 3. Okay, so we would say the limit was 3. And this line right here is a horizontal line with the equation y equal 3. It's called a horizontal asymptote. Okay, we've already dealt with vertical asymptotes earlier. Okay, this is the issue of horizontal asymptotes in this section. All right, now horizontal asymptotes are defined. Okay, so y equals some number. Okay, is going to turn out to be a horizontal asymptote if the limit of the function as you let x approach negative infinity equals that number, or the limit of the function as x approaches positive infinity equals that number. So note, the graph of that function can have two different horizontal asymptotes. It doesn't happen very often, but it can have two different horizontal asymptotes. One that shows what the function is doing to the right, and one that shows what's happening to the left. Now, not all functions will have horizontal asymptotes. Okay, you don't always have a function whose end behavior approaches a horizontal line of any kind. Okay, if you have rational functions, you oftentimes have horizontal asymptotes. If the function's rational, though, then it's going to have at most one. It might not have any, but it'll have at most one. Okay, so like this right here is an example of a rational function, and the function wound up approaching y equal 3, whether you're going to the right or to the left, so it just had one horizontal asymptote because it approached the same thing from the right as the left. We're going to look at algebraic techniques of determining that in a minute, but right now we were just looking at the graph. All right, here I want to show you an example of a function. Let's think about the function 1 over 1 plus e to the negative x. Let's think about that. So if I wanted the limit of that function, let's do the limit of f of x as x approaches, and let's go ahead and do a positive infinity. Then think about that. That would be 1 over 1 plus e to the negative infinity, because the infinity goes in for the x. So when I'm thinking about that, I'm thinking about how e to the negative infinity is the same as 1 over e to the positive infinity. Okay? And e to a bigger and bigger number is going to just get bigger and bigger and bigger. So what I've got right here, that 1 over e to the infinity, is like a fixed number over infinity. So this part right here is going to go to 0. So you wind up with 1 over 1, which equals 1. So as x goes towards positive infinity, the value of the function is approaching 1. But if we look at the limit of the same function as x approaches negative infinity, let's see what happens. Okay, then when I put in a negative infinity, I wind up having 1 over, let's see, 1 over 1 plus e to the positive infinity. So e to the positive infinity is just getting bigger and bigger and bigger, right? E to the positive infinity is infinity. You add 1, you've got infinity. So now you have like a fixed number over infinity. Okay? And that fixed number over infinity would equal 0. So with this particular function, when you're headed to the right, the function is approaching 1. So it has a horizontal asymptote at 1. And when you're going towards negative infinity, it has a horizontal asymptote at 0. Okay. All right, so let me just get the picture up here. So if I put a 0 in for x, that would be 1/2. So 0 is at 1/2. All right. All right, so it's doing something like this. It's going this way, and then this part is going here. So to one side, the horizontal asymptote would be y equal 1, and that's as you're approaching positive infinity. And then when you're approaching negative infinity, then the x-axis, y equals 0, would be a horizontal asymptote. So you can have two different asymptotes when you get to more complicated functions. Okay? All right. Let me go ahead and do just a little bit more. So the limits at infinity have a lot of the properties that we found out worked with the other types of limits that are approaching some number. So if you have a limit of a function as x approaches an infinity of some sort, say positive infinity, and the function might be maybe something composed of two functions being added or subtracted, multiplied or divided, okay? What you can do is do the limit of each piece, okay? You can, that's what I'm talking about when I say same properties. You know, what we learned before about how you could do the limit of just one of them and then the limit of the other one, and then just wind up, if it was adding, add, subtract. If it's multiplying, you multiply, or if it's dividing, you divide. So that kind of thing you can still do. And then here in this box, limits at infinity that are good to know, I just want to put in actual numbers so you have a sense of what it's really trying to say. So this one right here is really trying to say, if you're doing a limit and c is some kind of a number, any real number, okay, so let's say that c turns out to be 5, and you're dividing that, or let's make it negative, like a -5, and you're dividing that by x to some power that's positive. It might be any rational number, so it could be something like a 1/2, could be something like a 3. If you're doing something like that, okay, then that's going to wind up having a limit equal to 0, because imagine plugging in bigger and bigger numbers in for x. So infinity, cube root of it's still infinity. You square that, that's still infinity. So you basically have a -5 over infinity, a -5 over something getting bigger and bigger and bigger, which means that's going to wind up approaching 0. Okay, so that's what that says. And if it had been a negative infinity there, okay, here, then that winds up still giving you a 0 when you're finished. Okay, let me not change it over here. Okay. All right, so it can be a positive or a negative number over a positive or negative infinity, but it's the fact that the top number is something fixed and the bottom number is getting bigger and bigger and bigger that winds up causing the limit to equal 0 when you're finished. Okay. And then these two limits are ones that you can actually figure out by knowing that y equal e to the x looks like that when you're thinking about it. So if you had an e to the negative infinity, it means what's happening as you let x go towards negative infinity. And you can see how the e function is approaching 0. Or you could treat that as 1 over e to the positive infinity and think about e to the infinity is infinity. And so that would equal 0. So those are two ways to kind of ponder why that turns out to be 0 when you're finished. All right, and then this one, same deal. If you wind up having an e to the negative x and x is infinity, for the same reason as we just talked about, that would wind up equaling 0. Okay? And answers to these kinds of problems, if you have a function and you're looking for the limit as x approaches an infinity of any kind, okay, your answer might turn out to be, the possibilities would be that it could be some number, it could be negative, it could be fractional, okay, could be 0. It could also, though, it could be an infinity of some sort, like an infinity or a negative infinity. You can have all of those various things happen, okay? So here we're looking at finite limits, getting an answer that's just a number, or as x goes towards an infinity, getting an answer that's also an infinity. So on question number 1, if you think about it, if we plug in or imagine plugging in numbers that approach negative infinity, those negative numbers we're plugging in are getting squared, so that makes them positive. Okay, and an infinity squared is still infinity, and a constant over an infinity, that would go to 0, so this one's going to wind up having an answer of 5. Okay. On question number 2, we have a 3 over e to infinity, which would equal e to the infinity. E to a bigger and bigger number is just going to keep getting bigger and bigger, so that's an infinity, and a fixed number over an infinity would equal 0. So you can get finite limits when you wind up looking at the limit of a function going towards a positive or a negative infinity. Your answer might be something finite, like a 5 or a 0. Okay? But in these cases, when I'm thinking about this, I'm looking for the limit as x approaches negative infinity, and that more and more negative number is getting cubed, still going to be negative after I cube it, right? Still going to be negative. And an infinity times itself 3 times is still an infinity. So this one would wind up having a limit. It really doesn't have a limit, but we use the notation that the limit equals negative infinity. And over here, we'd have infinity to the 3rd power, which is still an infinity. Okay. And the graph shows us why that happens, because here's the graph of y equal x to the 3rd. So as you let your x go towards positive infinity, then you can see how the value of the function is getting bigger and bigger and bigger. So that's why that's the answer. And then as x goes towards negative infinity, you can see how the value of the function is getting bigger in magnitude, but in the negative direction.